Hi, I'm Jeff Groh and this is Calculus 1. Today we're going to talk about the Riemann integral. In our last lecture, we estimated areas of undergraphs using Riemann sums. We divided a region into pieces and then estimated the area by calculating areas of approximating rectangular strips and then added up those areas. We saw that as you make these strips smaller and you increase the total number of those strips, the accuracy of the approximation increases. This class is a class on applications of limits. We've done this with respect to the derivative, and we're about to do it again. What happens in the limit as the number of approximating strips tends to infinity? We should be able to find the exact area of the undergraph. Let's do a quick example. In this case, let's leave the number of subdivisions as a variable so that we can ultimately take a limit as the number of subdivisions goes to infinity. We'll progress in 3 steps. In the first step, we'll calculate delta x. It's the length of the interval divided by how many times you subdivide it. But in this case, n is a variable, and that gives 2 divided by n. Second, we need the elements of the partition, xk. The formula for that was a plus k delta x. In this case, a is 0, k is what it is, and delta x is 2 over n. So we'll end up with 2k divided by n. Third, we'll estimate the area by calculating the sum. It doesn't matter if you use right-hand endpoints, left-hand endpoints, or midpoints, so let's just use right-hand endpoints. Our function squares these values and then multiplies by delta x. Simplifying, we'll have the sum as k goes from 1 to n. We'll have this 2 squared times 2 is 8. K squared, we'll have an n squared times n. That gives us n cubed. 8 divided by n cubed can be factored out of the sum because it does not depend upon k. And this has a formula that I've asked you to memorize. In particular, it's n times n plus 1 times 2n plus 1 divided by 6. Simplifying just a bit, 2 goes into 8 4 times, 2 goes into 6 3 times. We have an approximation to the area of the undergraph. We can find the exact value of that area by taking a limit now, as the number of subdivisions goes to infinity. What's left over is this 4. We'll have n plus 1 times 2n plus 1 all over 3n squared. The numerator of this fraction is a quadratic with leading coefficient 8n squared. In the denominator, we also have a quadratic with coefficient of 3. In the limit as n goes to infinity, we take the ratio of the leading coefficients, which is 8/3, or 2 2/3. We're going to make a formal definition that's a little more general than what we just did. but includes the method that we just applied as a special case. The greater generality allows us to apply this method to a broader class of functions. The idea is like this. If you have some function, and this technique will apply to functions that are at least piecewise continuous. We'll talk about that later. We'll assume that you can divide the domain up into a partition, but that the subintervals don't necessarily have equal widths. We're still going to start at x0 and label them x1, x2, x3, and so on, but we won't assume that they're all the same distance apart. We'll have different delta x's. Delta xk will be xk minus xk minus 1, the distance between adjacent points in the partition. Now, in the past, we used either right-hand endpoints, left-hand endpoints, or midpoints as the places where we calculated the height of the approximating rectangles. We'll do something a little different here. We'll select points at random in here. We'll call them sampling points C1, C2, C3, and so on. The area will be approximately the sum as k goes from 1 to n of f of ck delta xk, but that's still only an approximation. This is slightly more general than what we just did and includes it as a special case. In order to set up the limit, we need to make the limit so that the number of subdivisions goes to infinity, but just sending the number of subdivisions to infinity isn't enough, because one of those subdivisions might remain big and hence give you a clunky and inaccurate crude approximation. You have to be sure that the largest subinterval goes to 0 in width. If the largest subinterval goes to 0 in width, then the total number of subdivisions will go to infinity. If P is our partition, we'll define the norm of that partition to be the maximum of the delta xk's within the partition. Maximum taken over all values of k. There's not just one partition. There's going to be a sequence of partitions as we make these subdivisions and get smaller and smaller. And so we'll have norms for each of these partitions. Remember, the norm of a partition is the maximum subinterval width. We're going to make the following definition. The definite integral of the function f on the interval ab, first of all, it's denoted by the following sequence of symbols. We say the integral from a to b of f of x dx. And defined as follows. The integral from a to b of f of x dx is, by definition, the limit as the norm of the nth partition goes to 0 of the sum as k goes from 1 to n f of ck delta x k. You can see we have a sequence of partitions that where the mesh size gets smaller and smaller. We're adding height times width. These are areas of approximating rectangles, but we're taking a limit as those rectangles get smaller and smaller. Before moving on, I want to caution you that this definition has absolutely nothing to do with antiderivatives. The old indefinite integral was by definition the class of antiderivatives. This has nothing to do with that. This is limits of Riemann sums. The definite integral that we have defined is also sometimes called the Riemann integral. It turns out there are several other kinds of integral that mathematicians have invented over the course of time. There's the Lebesgue integral and the Darboux integral and other kinds of integrals that people have invented. The Riemann integral being one particular kind. Let's do an example. Let's look at f of x equals x cubed, and let's look at the interval 0 to 1. The integral from 0 to 1 of x cubed dx is what we want to find. The first step is to calculate delta x. Delta x is b minus a divided by n. In this case, just 1 over n. The second step is to calculate the elements of the partition. And as you know, that's a plus k times delta x, a being 0. We'll have k times 1 over n, or k over n. Third, we estimate the area using a Riemann sum. So we'll write that as the sum as k goes from 1 to n. We evaluate the function at xk, which in this case is k over n cubed, and then we multiply by delta x, which is 1 over n. In this case, we can rewrite this as 1 over n to the fourth times the sum as k goes from 1 to n of k cubed. It is at this point we need to use that formula for the sum of k cubed. We'll have this 1 over n to the fourth, but it's going to be times the quantity n times n plus 1 over 2 quantity squared. Foiling this out, we get n squared, n plus 1 squared over 4 times n to the fourth. We do get a little bit of cancellation. We see then that the integral from 0 to 1 of x cubed dx will in fact be the limit. In this case, since delta x's are all equal width, sending the number of subdivisions to infinity is the same as sending the maximum subdivision to 0. And that's going to be the limit of n plus 1 squared over 4n squared. And since we have a quadratic over quadratic, we take the ratio of the leading coefficients, and we end up with an exact area of 1/4. There are certain questions we need to answer about this new concept, the definite integral. First, is there a nice class of functions for which the definite integral exists? It is possible to show that there are functions for which the Riemann's integral doesn't even exist as a limit. First, we say that a function f has a jump discontinuity at x equals a if both one-sided limits exist but are not equal. So if the function has a limit from the left and a limit from the right, but the limits are not the same, then the function has a jump discontinuity at that value. Remember, a discontinuity is called removable if both the left limit and the right limit exist and are equal, but either the function is not defined at that location or the function value is different than the common limit from each side. A function f is called piecewise continuous on some closed and bounded interval AB if it is continuous except at a finite number jump or removable discontinuities. So, if it has only a finite number of places where it jumps or has removable discontinuities, then the function is called piecewise continuous. Fortunately, if f is piecewise continuous, on some closed and bounded interval AB, then the Riemann integral of f on that closed and bounded interval AB exists. This gives us a generous class of functions on which we may work. You should also note that every continuous function is piecewise continuous, the number of discontinuities being 0, which is certainly finite. A classic function that is not piecewise continuous is the Dirichlet discontinuous function. Recall that that function is defined to be 1 if x is irrational, and 0 if x is rational. This function is discontinuous at each point in its domain. You'll recall that the irrational numbers and the rational numbers are interwoven. If you were to try to integrate this function between 0 and 1, if you choose your sampling points c sub k to be irrational numbers, then all of your approximating strips will have areas that go up to a height of 1 times whatever the delta x is. The area will end up being 1. If you choose all of your sampling points, c sub k, to be rational numbers, then those heights will be 0. You'll get different limits depending upon how you choose the sampling points, which means that this function won't have a well-defined limit for the Riemann integral. Therefore, this function is not Riemann integrable. It has too many discontinuities. We need to know something about the properties of this new thing, the Riemann integral. We demand a theorem. First, if you integrate from a to a for some Riemann integrable function f, you will get 0. What is the area under a single point? The answer is nothing. Also, if this function is bigger than or equal to 0 for all x between a and b, then the integral from a to b of f of x, this representing the area of the undergraph, can't be negative. Now, is it possible to have negative areas? We've defined this Riemann integral in such a way that if the function values are negative, the little delta x's will be positive. Negative times positive will give us negative areas. We're just going to allow that. How is the integral from b to a of f of x going to be related to the integral from a to b? Notice that our delta x's were calculated as b minus a over n, but we were assuming b was at the upper limit of integration and a was the lower. If you switch the order of the limits of integration, that's like switching the order of the subtraction, and it makes all of your delta x's negative. Instead of marching from left to right on that number line, your partition will march from right to left. And the relationship then is that these will be exactly opposite in sign. That's property 3 of the theorem. Property 4 of the theorem goes like this. If you have a function defined between a and b, and there's some number c in between, then the integral from a to b will give you the same thing. This is the area of the undergraph between a and b. It's the same thing as if you integrate from a to c and find that area of that piece of undergraph from a to c, and then add the area from c to b. There are a few other properties we need to add to this theorem. If f of x is bigger than or equal to g of x for all x between a and b, then the area of the undergraph for f of x will be less than or equal to the area of the undergraph for g of x. Obviously, if you take the integral from a to b of f of x plus g of x, you'll get the same thing if you integrate f and then integrate g. Similarly, if you integrate from a to b some constant times f of x, this constant can be pulled out. The proofs of these two properties follow from the similar properties for sigma notation. The proofs of these properties are all fairly simple, so I suppose we should at least prove one or two of them. Let's look at the integral from a to b of a constant times f of x. This is, by definition, the limit as the norm of the nth partition goes to 0 of the sum, as k goes from 1 to n, of c f of ck delta xk. Now this constant c can be factored out of the sum, and constants can be factored out of limits, which means the rest of this is just the integral of f. So you get c times the integral of f. That's the end of that piece of the proof. Other parts of this theorem follow in a similar fashion, just appealing to the definition and properties of sums and limits. It is very important that you understand the geometry of what we're doing. This definite integral is giving you areas of undergraphs, and you can calculate some of these using geometry. Suppose, for instance, I'm integrating from -2 to 2 the square root of 4 minus x squared dx. Let's think about this geometrically. Suppose I have a curve y equals the square root of 4 minus x squared. What kind of curve is this? If you square both sides, you get y squared is 4 minus x squared. Moving x squared over, you get x squared plus y squared equals 4. That is a circle of radius 2. But you don't get the whole circle. This is the principal square root. The principal square root does not give you negative values. It gives you non-negative values, which means you only get the upper half of this disk. The definite integral will give you the area of the upper half of a disk of radius 2. It follows immediately that the definite integral is half pi r squared. The area that we get is exactly 2 pi. We've noted that if a function is sometimes positive and sometimes negative, let's say between a and b, when we partition the function, we'll have sampling points where perhaps the curve is positive in some places, and other sampling points where we get negative values. Some of these areas, this area here will be a positive area in the limit, whereas this area down here will be a negative limit, a negative area. The negative area and the positive area will partially cancel out. When we integrate from a to b, we won't get all of this area. We'll get only a portion of the area that doesn't cancel out. As an example, consider the function f of x equals x cubed on the interval -1 to 1. Between -1 and 1, we expect to get a total of 0 when we integrate, because half of the interval will have negative area and the other half will have the corresponding positive area of the same magnitude. Similarly, suppose we integrate from 0 to 2 pi sine of x, and don't be leaving off my differentials over here. They have an important function, as you'll see later on in the course. The total area between 0 and 2 pi should exactly cancel out the positive bump and the negative bump, giving you a total of 0. If you integrate either sine or cosine over an entire period, you get nothing. A similar statement holds if you integrate cosine from 0 to pi. Remember, cosine starts up, goes down, and back up. Between 0 and pi, you have half a positive bump and half a negative bump. These exactly cancel out, and you get nothing. If you integrate from a to b some constant k, the function is constant at a height of k, and you're integrating from a to b. You must in fact get the area of a rectangle. The height of the rectangle is k, and the width is b minus a. So this must in fact be k times b minus a. I want you to remember this. As you can see then, if I integrate from 0 to 3, 5 dx, I'll get 5 times 3 minus 0, which is 15. If we integrate from -1 to 1, the absolute value of x, what do we get? This is easy to figure out by geometry as well. This is half of a square, split right down the middle. You can actually flip this over and form a full square. The area here being a half, and the other area on the right being 1/2 as well. As our next example, suppose I want to calculate the integral from 0 to 2 of x squared minus 3x plus 5. To calculate this, we're going to have to go through the entire steps, starting with calculating delta x. You know I'm going to have you do one of these at least on the exam. So this one should help prepare you. This is the worst conceivable case. I'll certainly give you something easier on the exam. Delta x in this case is 2 minus 0 over n, or 2 over n. The elements of the partition are 0 plus k times 2 over n, or 2k over n. The area then is approximately the sum as k goes from 1 to n, our function evaluated at the sampling points xk, that's going to be 2k over n squared minus 3 times 2k over n plus 5, all times delta x, which is 2 over n. We'll simplify this. 2 over n can come out of the entire thing. We'll break this into 3 separate sums. The first sum has 4 over n squared that can be factored out of the sum as k goes from 1 to n of k squared. 2 over n times 3 can be factored out. We'll have negative 6 over n, the sum as k goes from 1 to n of k. And then if we add 5 to itself n times, the last term is simply 5n. Now, using those formulas I asked you to memorize, we'll have 2 over n times 4 over n squared times n plus 1 times 2n plus 1 over 6 minus 6 over n times n plus 1 over 2 plus 5n. As you can see, we are going to get some simplification here, and we do still need to distribute this 2 over n onto each term that remains. If we do, this will be 8, this will be 12, this will be 10. This n is coming in, we'll get another n here, so it's back to n squared. We'll have an n down here, and this n will cancel. As you can see, what's left over is n plus 1 times 2n plus 1 over 6n squared minus, I guess 2 cancels here, giving us 6 n plus 1 over n plus 10. What's missing? I'm missing my 8. This 8 and the 6 can cancel. So we'll have a 4 in front there. Finally, we'll have the integral from 0 to 2 of x squared minus 3x plus 5 dx is equal to the limit as n goes to infinity of what we have above. 4 n plus 1, 2n plus 1 over 3n squared minus 6 n plus 1 over n plus 10. As n goes to infinity, 10 goes to 10, 6n plus 1 over n goes to 6, and over here we'll have an 8n squared as the leading coefficient on the top. We'll end up with 8 thirds minus 6 plus 10. 10 minus 6 is 4. 4 is 12 thirds plus 8 thirds gives us 20 thirds. By way of review, today we've defined a new object called the definite integral. The definite integral is calculated by calculating limits of Riemann sums. In doing these limits, we are calculating exact areas for undergraphs of various curves. We've seen that this definition works provided the function you're dealing with is piecewise continuous. It has nice properties and it's pretty easy to work with. It just takes a long time to do each of these problems. That means there has to be a better way. We're looking forward to a theorem that will allow us to avoid calculating all these limits of Riemann sums. Fortunately, that theorem is on the way.